Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing mathematical modeling. This is Chapter 2, Discrete Time Models. Section 2.3 is going to be solving higher order difference equations. This lecture, what we're going to do is we're going to do an overview of higher order k greater than or equal to 2 difference equations. If you want to remind yourself what the order is, watch the previous video. In particular, what we're going to do is focus on, for an introduction to solving higher order difference equations, we will focus on, because a lot of clever things we can phrase in order 2. This is order 3, this is order 2, but getting much higher than that, I don't think you'll need this practically. Basically what we're going to do is we're going to focus on solving constant coefficient second order linear non-homogeneous difference equations. Again, I'll go through what all of these are individually before we start, but in general what we're going to do is focus on linear first of all, because non-linear is extremely difficult. Then what we're going to do is, at first we're going to make sure all the coefficients in front of all these terms are going to be constant numbers, not functions of time. And then we're going to focus on degree 2 or order 2, which means that we're going to xt will depend on only 2 previous ones. So order k means you depend on k different previous timestamps. Let's get to it. All right, before we start, definition. A linear constant coefficient difference equation is a sequence of real numbers, these guys. So it's a way to compute, and it's going to have a specific real value in every stage, such that the tth term, or the xt, is going to be defined through the previous terms, xt minus 1 to x0. These are going to be, and if we're going to solve explicitly and have the unique solution for this closed form for the difference equation, what we mean is you have to be given initial conditions. So we fix the first t minus 1 values, and then we're going to use those to specifically find the coefficients and everything that we need for this specific solution in the homogeneous part and the particular part in this general scenario. So what is this? It's if we're going to have linear and constant coefficient difference equation, we already know what that is, hopefully. If not, go look at the previous videos. But a linear constant coefficient means that linear means every term is just a function of time, or function of time times a single variable. In this case, our variables are the xt's. If we do constant coefficient, what that means is the only function of time is going to be this f of t part. All of these guys are going to be, I think I used these as a's last time, now they're c's, but they're going to be c for constant. They're fixed numbers, so they're all real numbers also. This is what we mean by linear constant coefficient. It's going to have this general form. And then the idea is, if this guy is 0, we call it homogeneous. If it's not 0, it's non-homogeneous. And what we're going to see right away is, and produce several theorems about this, is that the general solution to this form is going to be a linear combination of the homogeneous solution associated to the homogeneous equation when we make this 0 specifically, and then some particular solution to the non-homogeneous equation. Once we figure out a way of finding this guy, and then figure out a way of finding this guy, the general solution to this is always adding those two things together. Let's get to that. All right, I had to bring the kitties in because they were learning how to jump the fence. Bad kitties. Now she's tired. Alice is going to sleep in my arms while we try to do this. All right, so we're trying to solve this order k linear constant coefficient non-homogeneous difference equation. This is its general form. We're not going to do in this course where we have non-constant coefficients. We'll just leave it to where the first time round we're going to do, these will be constant fixed numbers, which is good news for you, trust me. Then what we're going to do is, unfortunately, at first we're going to assume he's 0 and see how to do that. But what we're also going to do is we're not going to do general order k. We're going to focus on order 2. So it'll only be 2 of these terms. It won't be dot, dot, dot. There won't be a whole bunch of those, so it's not too bad. Finding the roots of polynomials for degree 3 and higher is hard. Look at Galois theory, essentially. But what are we doing here? This is what we want to solve. This is called the order k linear constant coefficient non-homogeneous equation. Immediately associated to that is, once you see the technique at the bottom here, we want the homogeneous. So if we let this be 0, what we're first going to do is pretend that function is not there and see if we have a systematic way of solving the homogeneous one. So we immediately get an associated number 2, associated homogeneous equation. So it's the same first part, but the only difference is we're killing the f of t for temporarily and solving this guy. Then we use this solution as part of the solution to this guy. Oh, you're awake now? You want down? Okay. Bye, kitty. When the kitty wants to snuggle, you gotta pause for a second. Snuggle. She's done now. Oh, she's gonna attack my feet at the bottom. She's down there. Well, come back then, silly. Why were you so wiggly? She wanted to come back. I guess she didn't get enough snuggles. What the idea is going to be is, here's our terminology. We're going to call a particular solution xt part for particular to equation 1 is going to be any function g of t which actually satisfies this thing, which makes it true when we plug it in there. So that's going to be any particular solution. We're going to give you with some certain special nice functions a clever way using a method of undetermined coefficients to find these particular solutions. So that's how we're going to find it. That's our question at the end. I've just answered that. So, and then the other notation that we need is xt hom, which is going to be for homogeneous. We're going to immediately kill that one in our technique and solve the associated homogeneous equation. And the general solution to the associated homogeneous equation 2 is going to be called the homogeneous part, or xt homogeneous. Once we have that, the general solution to this equation is going to be a linear combination of any particular solution and the homogeneous part, and the general solution to the associated homogeneous equation. Once we have that, this will be our notation. The general solution is going to be xt particular plus xt homogeneous. The homogeneous one, we're going to get a technique for systematically finding that. The particular solution, this is non-trivial in general. This is why we start with homogeneous and then we get there. But I have several clever forms where at least we can have a technique to solve and find that particular solution. Once we do that, we can solve any kind of order k, but we'll focus on order 2 difference equations and how to solve and find their general solution. So the question you should be asking yourself once we do a whole bunch of this and after you organize all of this terminology is, how do we find this? I claim somehow magically is the general solution always. So we want to know systematically how to find the homogeneous part and systematically how to find the particular part. Let's get to that. Right? All right, so what we're going to do first is let her chew on my fingers, I guess. And then we're going to solve homogeneous linear constant coefficient order k difference equations. The idea here is extremely clever, and then we have half of the battle. Once we know how to find xt homogeneous and xt particular, we have the general solution to all of these non-homogeneous equations. So this is the associated, or just in general, if you're given one, if the f of t is 0, this is the homogeneous equation. What we're going to do is assume cleverly that the solution is r to the t for some non-zero base r. Then what that does for us is give us our associated characteristic equation. That's going to be hidden in here, and then everybody forgets where it comes from or how to build this, but it's going to be in this clever substitution. If I take that guy now, and then x to the t minus 1 is going to be r to the t minus 1. And x to the t minus 2 is going to be r to the t minus 2. And if I take all those values and plug them back in here now, I'm going to get xt is r to the t. Xt minus 1 is r to the t minus 1, all the way down to xt minus k is going to be r to the t minus k. Luckily, the best part about this is factoring polynomials is extremely hard, but factoring this one originally is going to be fairly easy. First of all, what I'm going to classically do is move everything to the left-hand side and write it equals 0. And so this is if and only if this guy. And then I notice that in every term, I have at least one r. So what do? You pull out the lowest exponent of r appearing in every term, which is going to be t minus k in this case. So I can pull out t minus k out of every term. When I do that and do the algebra with all the exponents, I'm going to get r to the k minus this sum of ck minus 1, r to the k minus 1, dot, 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 c plus c0. This thing right here in a second is going to be what we call our characteristic equation. Why? Because we start with this and we're going to assume cleverly that this is our solution. This is a solution if and only if this is true. If and only if this is true. If and only if this is true. R is not 0, so R to the t minus k can't be 0 either. So what that means is this has to be 0. Therefore, this is a solution to this equation if and only if R satisfies or is a root of this polynomial. And this is what we're going to call the characteristic polynomial of this difference equation. Let's write that and then solve a couple of these. To recap, we have a homogeneous difference equation, linear constant coefficient order k, blah, 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 blah. It's going to be the same always, order 1 and order 2 primarily. Once we do that, we have if and only if this is 0, we move everything to one side, factor out the r. And then what we see is because this guy can't be 0, this has to be 0. So if and only if what we're going to call p of r, this polynomial in r is 0. What that tells us again is if we assume that x to the t is equal r to the t is a solution, if and only if this polynomial is 0, but this can't be 0, so if and only if this characteristic polynomial is in fact 0. And what that says is r is a solution for our difference equation if and only if r is a root of this characteristic equation. Therefore, what we have to now do is what Galois shows is impossible for degree 5 and higher polynomials in general, but we want to factor polynomials, find all the roots, and then we can phrase based on what kind of roots we get the general solution to these difference equations. When we do order 2, that means that there will be a degree 2 polynomial, which means we can use the quadratic formula, and we will always have 2 distinct real roots, a double real root, or 2 complex conjugates, and then we can phrase the solutions on that, and that's what we're going to focus on in this video and in this course primarily is order 2, so then we can luckily use the quadratic. When we do order 3, you better hope that you can factor this polynomial somehow, otherwise we're stuck at that stage and we can't go further and explicitly write down the general solution. So on top of everything else, somewhere along the way we have to factor polynomials of degree k, which can be sucky, so we'll stick to order 2, and then we know we have the quadratic formula. Secretly, that's sort of why. Alright, once I have that guy, this obviously is going to get a fancy name, and so we're going to call this the characteristic polynomial of the homogeneous difference equation. Let's do an example, and then we'll state the general theorem for this, and then we'll do a theorem specifically about order 2. As a first example, we've already discussed in the previous video first order difference equations, so let's solve one of those. It is a constant coefficient. It is linear because I either have a term that involves xt, a term that involves xt minus 1, or I don't have any terms that involve functions of just time, therefore it's also homogeneous. So this is a first order linear constant coefficient homogeneous difference equation, and I have an initial condition. The first thing I should point out as we do this, and right after this I'm going to state the general theorem for homogeneous solutions. If you're not given initial conditions, then you have to leave the solution up to constants. You can leave the most general solution is going to have these variables in there which we can't find. If you specifically have the initial conditions, we can use our clever technique to actually find explicitly what those constants are, and we'll have a unique solution to these difference equations. I'll do that specifically here, and then I'll point it out as I go. What we're going to do is solution. We're going to assume, just like we did in the general form, but it's first order now, I'm going to assume that xt is r to the t. If I put that in here now, that's going to give me r to the t equals 2 r to the t minus 1. I'm going to bring everything to the other side like I did, but in the general formula, like I don't like what's happening. So here, what I'm going to get is r to the t minus 2, r to the t minus 1 equals 0. And remember, k is 1, so we can pull out the lowest exponent will be t minus k, or t minus 1 in this scenario. So I do that. This is if and only if r to the t minus 1 times r minus 2 is equal to 0. Now we're assuming, obviously, that r was not 0. So this can't be 0. If this product is 0, that has to say if and only if r is 2, or r minus 2 is 0. That tells us we have a unique root here in this case for this characteristic polynomial. Our characteristic polynomial p of r is r minus 2 in this case. It has the unique root r equals 2. What that tells us is the general solution going to be xt is going to be some constant times 2 to the t. But I also know that x1 is 1, and I can use this initial condition to find, I use that to find c. What is that going to be? That tells us at timestamp 1, we have the value 1, and then now we can have an explicit formula and we can solve for 1. So this is telling us 1 is equal to x1. But on the other hand, if I put x1 in here, this will be equal to c1 times 2 to the 1. And now I can solve for c1 in this equation and I can get the unique solution. That's going to tell me that this tells me c1 is going to be 1/2. This tells me that the general solution with the initial condition specifically is going to be x to the t is going to be 1/2 times 2 to the t, which is coincidentally 2 to the t minus 1. This is how we solve using the initial conditions and this clever substitution, or the characteristic polynomial, how we find the general solution to homogeneous difference equations. Now let's state the general theorem and then I'll do some higher order ones. Alright, theorem, the main theorem for homogeneous linear order k constant coefficient difference equations. These guys, how do we solve this? Assume that we're given this equation. Assume that this is our associated characteristic polynomial by cleverly assuming that our solution is r to the t. And assume that, even though this is extremely difficult, I'm going to make you do it if you're in one of my classes. Factoring degree k polynomials is not trivial in general, but assume that I've factored that polynomial and found all the roots of it and that we know what the multiplicities are. I'll do what the multiplicity are, the algebraic multiplicities are in a second, but that's the number of times the root appears in the polynomial. So if you have r minus 1 squared, the multiplicity is 2 because it appears twice, r minus 1 times r minus 1. If you have all the roots and their multiplicities explicitly, then we can cleverly, and I'll show you right away in an example so we can clarify this theorem somewhat. The general solution is always given by x to the t is a polynomial times the first root to the t plus dot 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 all the way down to another polynomial pl times the lth root rl to the power t. This will always be the general solution, where these pi's are polynomials of degree mi minus 1. So the multiplicity minus 1 every time will be the degree of these polynomials, and we're going to explicitly find the polynomials and their coefficients. If you're not given initial conditions, right here, obviously we also have to have x0 is alpha 0 to xt minus 1 is equal to alpha t minus 1 are fixed numbers. If you're given the initial conditions, then I use these initial conditions, these numbers that were given, to explicitly find all the coefficients and all the polynomials. If you're not given initial conditions and it says solve it, then the general solution, you'll leave all the coefficients of the polynomials there, but you can still find out what the degree of the polynomial is multiplied by these roots. Let's do an order 3 difference equation. All right, example 2, solve the third order linear constant coefficient homogeneous difference equation. It is order 3 because xt depends on the previous 3 terms, xt minus 1, xt minus 2, and xt minus 3. It is linear because every term is a multiple of a single one of these xt's, or a term that is just a function of time entirely. It's constant coefficient because all of those multiples are constant fixed numbers, and it's homogeneous because we didn't have any terms that had just t involved in them. We also have initial conditions. Because it's order 3, we have to know, and if this is why I always do this part as well, just to remind you, this calculates a sequence of numbers, but you have to have the first 3, otherwise you wouldn't be able to put this in there. But now, when I want to calculate x3, I know what x2, x1, x0 are, so x3 would be 4 times x2 minus 5 times x1 plus 2 times x0. And that's how we're going to compute. So I like to remind you, and that's why I've listed them, using this definition, and this is a good check at the end when we do this, and we do all this big fancy theorem, and you use these formulas and you plug it in, you're like, did I get the right closed form? Well, but from the definition of the difference equation of the recurrence relation, we have that x0 is 0, x2 is 2, the first 3 are not too bad, x3 or x2 is 3, those were given. How do I compute this one? x3 now is what I just said, is going to be 4 times x2 minus 5 times x1 plus 2 times x0. And that's going to be 4 times 3 minus 5 times 2 plus 2 times 0, which is 12 minus 10, which is 2. And that's why I get x3 is 2. If you can keep computing, you can see now if I wanted to know what x2020 is, I would have to compute all the way up to x2020 and then recursively do this every time. x2019 is x2018, 4x2018 minus 5, blah, blah, blah. I don't want to do it that way. So the idea is, and what we mean by solve is, we're going to get a nice closed form, and then at least we only have to do one horrible calculation. Therefore, I like to remind you that this recurrence relation or this difference equation is computing a sequence of numbers that goes on and on and on. Now let's get the explicit closed form general solution for this difference equation. What are we going to do? We're going to, and I'll go through the whole rigmarole of the idea and the proof of what the theorem is doing. The theorem says cleverly, assume that xt is r to the t where r is not 0. All right, then I'm going to plug that in here. That says we're going to get if and only if r to the t equals 4 r to the t minus 1 minus 5 r to the t minus 2 plus 2 r to the t minus 3. I bring everything to one side. If and only if I get r to the t minus 4 r to the t minus 1 plus 5 r to the t minus 2 minus 2 r to the t minus 3 equals 0. I see that I have r in every one. I pull out the lowest exponent. This is going to be if and only if r to the t minus 3 is equal to r cubed minus 4r squared plus 5r minus 2 equals 0. I had to sneak it in there. This can't be 0 because r was not 0. Where did it go? R is not 0, so multiplying r by itself t minus 3 times isn't going to give us 0 either. That means that the characteristic polynomial has to be 0. This means that p of r is r cubed minus 4r squared plus 5r minus 2. And if you do a little bit of long division, I'm not going to do it in this video, but we'll see that this is r minus 1 squared times r minus 2. This is the characteristic polynomial factored completely. What this tells us, first of all, is r1 is going to be 1, and it has multiplicity 2 because it appears twice. And so this is root 1, and this is multiplicity 1 of the root 1. And r2 is going to be 2, and it only appears once in here, so the multiplicity is going to be 1. That tells us right away already, that tells us that in the general solution, this P1 polynomial is going to be degree 1. Because it'll be 2 minus 1. And this P2 polynomial that I'm going to get is going to be degree 0, or a constant. Once I know that, let's now build this general solution from this information. All right, moving that up, what have we got? We took this order 3 difference equation. We found the characteristic polynomial. We factored that characteristic polynomial and found the roots. The first root, we have 2 roots. That means our general solution is going to have 2 terms. And there's going to be polynomial times root 1 to the t plus polynomial times root 2 to the t. Our roots were 1 and 2 respectively. So r1 is going to be 1 and its multiplicity was 2. That tells me immediately from the theorem that the degree of that polynomial, and the guess I'm going to make, is going to be a degree 1 polynomial. The general form of a degree 1 polynomial is going to be at plus b, if you don't want to use indices for the coefficients. And this one, it says the polynomial standing in front of the 2 to the t is going to be a degree 0 polynomial. A degree 0 polynomial means it's a constant or a fixed number. What that means is the general solution, the theorem tells us, the general solution is given by x to the t is equal to p1 of t 1 to the t plus p2 of t 2 to the t, because these are my 2 roots, and then there's polynomials, and these here's where we get the clever guesses. P1 of t is going to be, we know it from this calculation that it's going to be degree 1, but we don't know what the coefficients are, so the most general form of a degree 1 polynomial is going to be at plus b. And P2 of t, we know and have the calculation that it's going to be degree 0, so we're just going to have that it's some real number, degree 0 polynomial. This is where we make the guesses. Now, how do I find these coefficients? Because we were given initial conditions, what I can do is look at these guys, but now use what I think my general solution is. So first of all, what does that tell me? Right now, here's the general solution and what you can leave it as if I don't give you initial conditions. If you are given initial conditions, you have to keep going and find out what A and B and C are. We're going to have a 3x3 linear system, and then we're going to augment a matrix and solve for this. What does this tell us? This is going to be AT plus B 1 to the t, which is just a 1. You can make that go away. I will in a second. Plus C times 2 to the t. And of course, in this one, I wish that root hadn't been a 1, but because that is like that, it's going to end up looking like this. This will be our most general solution, but let's leave the 1 to the t in there for now. That's what the theorem is saying. In a polynomial times the first root plus a polynomial times the second root, there was only 2 roots. This will be the general solution. If they didn't give initial conditions, this is where you would stop. But of course, for myself and for my students, you're going to get initial conditions. Find A, B, C. Let's do that. So this is the guess of the general form of the solution to this order 3 linear constant coefficient homogeneous difference equation. What we cleverly do is now use the initial conditions and then plug in when t is 0, 1, and 2. So we know that 0 is x0, but then if we put 0 into there using this definition, we're going to get 0a plus b, and then 2 to the 0 is 1, so we'll get a c. So that says we're going to get b plus c is 0. And then same thing, if we put that in there, we're going to get 2 is x1. If we put 1 in there, we're going to get 1 times a plus b, and then 2 times c. And we get this equation. And so we're going to get 3 equations and 3 unknowns, and it happens to be linear. Therefore, I'm going to, as a Pavlovian reflex, I'm going to augment the matrix, reduce it to REF, and then tell that I have a unique solution and find the values of those A, B, and C. What does this tell me? This tells me that I'm going to put these in a clever order. I'm going to put this equation in first just to be cheaty. So this is going to be 1, 1, 2, 2. The next equation, I'm going to also cheat and do this. This will be 2, 1, 4, 3. And then I'm going to put this one in there because I've already got a 0 in that spot. I noticed I have 0, 1, 1, 0. Once I do that, I am going to, if you don't know what I'm talking about, you're going to have to go watch our, we have a whole other playlist on this channel. It's Linear Algebra 1, and it's systematically in Chapter 1. We systematically do solving systems of linear equations, so go look at those ones and how to augment a matrix and put it in REF using Gaussian elimination. I'm going to get rid of this 2, get a leading 1, kill below. So this is going to give me 1, 1, 2, 2. I'm not changing the other row. Copy that down quickly. And then I'm going to get 2 minus 2 is 0. That's why I did it. 1 minus 2 is negative 1. 4 minus 4 is 0. 3 minus 4 is minus 1. Then what I can do is this in REF? Not quite. I'm going to get 1, 1, 2, 2. I'm multiplying by negative 1, or add them first. When I add these, I'm going to get 0, 0, 1, negative 1. And then here, I'm going to get 1, 0, 1. What that tells us now is, first of all, this is REF, row echelon form. I now know that I have a unique solution. That says that, who was the last one? C is negative 1. B is equal to 1, and A is equal to 2 minus B minus 2C, which is equal to 2 minus 1 minus 2 times minus 1, which is 3. So that tells us A is 3, B is 1, and C is negative 1. There, I found the 3 values. What does that tell us? That tells us that the general solution xt is equal to, what do we find? 3t plus 1, and this was a negative 1 minus 2 to the t. This is the most general solution. If you don't believe it, let's arbitrarily pick one. scroll back a little bit, and at the beginning of the question, this is why I did this. I listed a bunch of the sequence. The sequence was, where did it keep going? From here, it kept going. X3 was a 2, and then X4 dot 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 dot. So if we want to check and see if this is computing the same thing, let's see if we got it right. Using our now closed form, X3 we're computing is going to be 3 times 3 plus 1 minus 2 to the, what are we doing? 3, which is going to be, what did we get? 9 plus 1 minus 8, which is 2. Oh, we got the same number. So if you're still suspicious, calculate a couple more. You should get the same numbers. I think it was negative 15 or negative 3, negative 15, negative 45, a bunch of numbers. But this is how, once you get it, you can check using, you have the recurrence definition of how to compute these numbers. And then once you solve it, we assume that we have a closed form, which is actually computing those numbers too. Compute a few and match, and then you have a check to see whether you've done this correctly. That was homogeneous difference equations of order k. Now let's look at and phrase quickly, before we end this video at least, how we do non-homogeneous version of this theorem. Alright, to end this video, what we're going to do is the non-homogeneous theorem, and then I'll do one example of the Tower of Hanoi, which we saw in the previous video. So I'll use the new technique instead of using the horrible product and sum product formula for the non-homogeneous ones that I did for the first order in the last video. I'll use this theorem, which should still apply. They're going to be unique solutions. If you're given initial conditions, they're unique solutions. So whichever technique you use, it has to be the same. Therefore, what does this theorem say? Consider the non-homogeneous difference equation, this guy where we've added the f of t and that's not 0 explicitly, and then we have our initial conditions. Again, just like in the homogeneous case, we have the associated characteristic polynomial p of r. Assume that we've factored that, found all the roots and the multiplicity of those roots. Therefore, the general solution of the non-homogeneous equation is going to be a linear combination of the homogeneous part, where I let this be 0 and solve in the last theorem what we did, and then plus a particular solution, and then we're going to use this last bit to explain how we, for certain special kinds, in general this is non-trivial, find a particular solution, so then your hands are up in the air again, but at least for these nice forms of functions, I can explicitly give you the particular solution, and then therefore we'll have an explicit solution for the general closed form of non-homogeneous difference equations. What is this? Basically, the homogeneous part is, from the last theorem, those polynomials times each of the roots to the power t, and then these polynomials are of degree multiplicity minus 1 in each case, just like in the last theorem. And then we say, how do I find this particular part? This was half of this is the general solution. This is half of the battle. What's the other half of the battle? It's this last statement. If you have that this, see, I was copying it from someone else's notes, and that's what happens. The key to ingenuity is hiding your sources. So, if you have a function of t, not n, see, oh no, he should have been a t also. Now what's going to happen is, if I have a function of t, which is non-zero, but if it has this nice form where I have some other base s, which is non-zero, to the exponent t, and then times a polynomial basically. And then unfortunately, yes, I've used lowercase b's and then uppercase b's, and it looks like you made the same. Yes, if you have basically either, you can do 3 cases in the PDF that I attach or pin below. It will have 3 cases in this theorem. I just wanted to squish it into one. But if you have just an exponential function, s to the t, you could have guesses. If you had just a polynomial, you could do guesses, or in the most general case, multiply them together. If you have that your non-homogeneous part is an exponential function times a polynomial, what you can do is you can make the guess in 2 scenarios. Now this is where you have to be careful with certain ones. If this base s is not a root of the original characteristic polynomial of the associated homogeneous equation, then you just make the same straight up guess. If this is the non-homogeneous part they gave you, you make your guess that your particular solution looks the same, and then you plug everything in cleverly and use undetermined coefficients and find all those values. If s is a root of that characteristic polynomial of multiplicity m, then what you're going to do to keep these linearly independent again is you're going to multiply by t to the m, multiplied by that guess. So if it's not a root, you just make the same guesses, the same form, but you're going to put undetermined coefficients bk to be 0. If it s happens to be a root of multiplicity m, you multiply by t to the m of the guess in part 1. Let's do a first order example. Then next time what we'll do in the next video is we'll restate the theorem. We'll do this specifically for the non-homogeneous and homogeneous theorems for order 2, because then it'll be quadratic, and we'll do a whole bunch of examples. But I'm sure you're done with this video, and I want to do 1,000 more, but we don't want 3-hour-long videos. Let's do one more example. All right, example 3, the number of moves, the minimum number of moves to solve the T-ring Tower of Hanoi puzzle. We actually have a video, so go find it somewhere. There's a Tower of Hanoi puzzle video that we did. The minimum number of moves to solve the T-ring Tower of Hanoi puzzle gives us this difference equation. Xt equals 2xt minus 1 plus 1. So what they're saying is you have to move them. There's these 3 pegs, and then you have these rings on there. If I do the 3 ring, can you move these onto there such that you can't put a larger diameter ring on top of a smaller diameter? And you want to see how to play this game. But the idea is what you have to do is to move this over there. What you're going to have to do is solve the 2-ring puzzle and put it there. And then move the 3rd ring over. There's what the 1 comes from, the 1 move. And then you're going to have to do this, the moves for 2 rings, and you're going to have to move that guy over there, and then this one, and then you can move it over. So what this is saying is once you analyze this game, you get this difference equation. Now how do we systematically use that horrible non-homogeneous theorem to solve this first order non-homogeneous constant coefficient linear difference equations? What we're going to do is, first of all, the homogeneous part. What we do is, and that you will like this a lot, we kill the function. So that's just going to be xt minus 1. We've already done this one, but let's quickly do it again to remind us, now that we have this more terminology, the characteristic polynomial and everything else. This immediately says that we're going to guess that x to the t is r to the t, and this will give us our characteristic polynomial r minus 2 equals 0. That's going to be if and only if r equals 2. So we have one root to our characteristic polynomial, and it's multiplicity 1. What that tells us is the general solution to the homogeneous is xt homogeneous is going to be c1 times 2 to the t. Sorry, this cat's harassing me down there. All right, where were we? Now we have the homogeneous part, and we don't find c1 till the end. Now what I need is the particular solution. And this is the new part from the theorem. How do I get this? What I'm going to do is my polynomial f of t is still just a constant function, 1. So what we're going to do is, this is actually 1 to the n. So this is s equals 1. This is what the theorem is talking about. Pay attention. What this tells us is, I look at now my characteristic polynomial, s equals 1, I'm trying to make a guess. S equals 1 is not a root of this characteristic polynomial. To make our guess, therefore, we have part 1 of the theorem, which tells us that our guess is going to be xt particular is going to be equal to, also this is 1 to the n times a degree 0 polynomial, the number 1. So what we're going to do is it's going to be, our guess is going to be 1 to the n times a general degree 0 polynomial, which we don't know, which is the number b, which is a constant, and therefore we're assuming that xt particular is just a constant number b. Therefore, what that tells us also is xt minus 1. You don't have to write the particular every time, we're just trying to find this particular solution. Xt minus 1 is also going to be b. If you had a higher order one, they're always going to be b. It's going to be the constant number every time. Therefore, what does this tell us? From our non-homogeneous equation now, what that tells us is b equals 2b plus 1, because I put xt there and xt minus 1 there in the definition. And then what do I see? This tells us that, bring the 1 to the other side and this one to this one, it tells us b is negative 1. Therefore, what did we get? This tells us now that our xt particular is equal to negative 1. And then now we get a linear combination of that. What does that tell us? That tells us our general solution is going to be xt equals c1 2 to the t minus 1 plus our particular part. And then let's get rid of this kitty and I'll move everything up and I'll show you how to use the initial conditions to find the c and then write out explicitly the general solution. Right, kitty? Right. All right, I moved everything up. I couldn't get rid of the cat, but I moved everything up. What does this tell us? Let's recap. I've got xt homogeneous was c1 2 to the t. We then cleverly found a particular part, our particular solution, which was -1. That says the theorem tells us that the general solution is xt homogeneous plus xt particular, which is c1 2 to the t minus 1. Because they actually gave us the initial condition x1 is 1, we have a starting point. How many moves does it take to move one ring? 1. Solution. With 2 it already gets crazy. All right, now she wants that. Oh, she sees the cat. You want the cat? All right, what do we do from that? From the initial conditions, we know that 1 is equal to x1, and then I put that into 1 into this definition, or into this closed form. That tells us that will be c1, 2 to the 1 minus 1, which tells us that we're going to get what? This tells us move this to the other side. 1 plus 1 equals 2c1, which implies that c1 is in fact the number 1. And therefore, the general solution is given by x to the t is equal to 2 to the t minus 1, just like we found using that horrible product formula from the last video. Either way, whichever technique you use or whichever method you get, using the initial conditions and this method, you can get the unique closed form, which is a Mersenne number. In particular, the Mersenne primes. If this number is a prime number, it's called a Mersenne prime. But this is the number of moves. It's a closed form. Now, if I want to know how many moves it takes to do the 16-ring Tower of Hanoi, it's going to be 2 to the 16 minus 1, which is an abhorrently large amount of time. I know, we're done. Just a second. She says we're done. I guess we're done with this one. What we're going to do, I was going to do another video, or I was going to do another example, but I'm already getting my words mixed up. It's not another video, it's another example. Therefore, what we're going to do is, and here, next time what we're going to do is we'll do the general theorem of homogeneous and non-homogeneous for order 2 specifically, and then we have the quadratic formula at least, and we can phrase this a little bit better, and then we will do a whole bunch of examples. Please subscribe right here. I will see you next time.